All right, so this is section 11.8. We're talking about power series now. So we've gone through all of the series tests for convergence and divergence that we can do. So now we're going to put it together with this thing which is called a power series. Um, in general, the easiest way to think about a power series is that a power series is the same thing as a regular series, except now we're including a variable x. So we're actually making this a function of x. So we're making these series functions of a variable now, and the variable is going to be x. To start talking about the ideas of power series, we're going to talk about a couple of topics which are called the radius and intervals of convergence. That's really what we're going to talk about here in 11.8. We're going to take power series to a little bit higher levels as we go on through the rest of the chapter. So, as I mentioned, a power series is like a regular series, but now it has variables. I want to try and give you somewhat of an idea of what it is that we're looking at. You can read the rest of that paragraph if you want to, but the general idea is this. When we have a power series, which is now a function, what we have is some kind of a series, whatever the series is, based upon a function. A series can be convergent with a power series in three different ways. And by the way, a power series will always be convergent somewhere. The general concept is this. If I were to have a series, whatever the series does, maybe it looks like this. A power series could be convergent with that specific series, whatever that is, at one point. Okay, it is quite possible that it's only going to be convergent at one point. So maybe whatever this thing does, the power series, this is not a good drawing. Let me try again. The power series might only touch, let's do it up here, might only touch that series at one point and then maybe bounce off or something and do something different. So your power series might only actually touch right there. And that one point is what we call the center. Okay, that's actually what this C right here represents in this function, the center. It is also possible, and I am going to erase, no, I'll just draw another one on here. It is also possible that a series could converge for the entire thing. So maybe this is what our series looks like, and then we create this power series, again, some kind of a function, and every single possible point along here matches with what we've created by our power series. That just means that the series converge or come together at every single possible point. So that would be an infinite convergence. In other words, the series would converge from negative infinity to infinity. Every single possible value of x would work. And then we have a third possibility. And that third possibility is that, once again, we have some kind of a series, whatever this series looks like. And I'm doing this to, just kind of show you in general. These probably not going to look at all like these during the regular thing here, but it could be that the series comes down here, it starts to converge and match the other series for a while, and then they start to diverge after that. So basically what you would have now is you would have some kind of an interval of convergence. Excuse me, and that interval of convergence is actually going to have an equal distance away from its center. So the center might actually be represented by letter C right there, whereas the C up here is here, and the C over on the other one could be anywhere because literally it converges at any possible point. So you could put the C anywhere, but it's not going to matter. So you could have an interval of convergence which maybe only goes from here to there or something like that. So that's what we're going to start to try and figure out. First of all, what is the radius of convergence? The radius of convergence is the distance from the center to its furthest point where it is still convergent. So like in this case, you would go from C out to here or C that way. It should be the same distance. That would end up giving you the radius of convergence. In a situation like this, the radius of convergence is technically 0. It is just convergent at its center, so there's no radius there. And in something like this one, the radius of convergence is infinite because literally it goes on forever in either direction and it's always convergent. Okay, that's a lot of background before we actually get to how to do these things. How to do them is something, fortunately, we've been doing now by doing the ratio test. And that's going to be the primary test that we use in order to figure out the radius and interval of convergence. So again, here are your three possibilities. Only convergent at the center, that's number one. The series converges absolutely for all x, and that's number two. And then the series is going to converge in between two possible bounds. All right, let's jump into the second page. So here's the way it works. You're going to use the ratio test in order to figure this out because this is a test for absolute convergence. So we're going to use the ratio test because that's probably the easiest one to use with some of the crazy functions that we're going to have to deal with here. All right, so the first thing we'll do is we'll set up the ratio test just like we would when we were doing it with just regular series and we were just dealing with n. But we will have an x involved here. So if we go through the whole process, simplify it out algebraically, find the limit, and we find that our limit approaches 0. Well, if you remember the criteria for the ratio test, anything where the limit of the absolute value gives you a value less than 1 is going to be convergent. Well, 0 is obviously less than 1. If that's the case, that means it's not going to make any difference what you plug into x. It will always be a convergent series. So everywhere, infinity. If the limit is infinity, well, that number is definitely, well, infinity is not a number, of course, it's a concept, but infinity is definitely greater than 1, meaning that the series is only going to converge at its center. It's the only possible value that would actually make it convergent. And then if you have neither one of those two things, you're actually going to be able to set up an inequality to find the actual intervals and radius of convergence. And we'll go through all of that stuff as we go through the problems. Let me preface this by saying, after we do a certain number of examples, you may not need to watch every possible example. I'm going to run through them, so the videos might get a little long, but you may not have to watch every single one if you're starting to get the idea behind this. All right. Again, just a reminder, series converges absolutely if the limit of the absolute value of the common ratio is less than 1. It's going to diverge if the limit of the absolute value is greater than 1 or infinity, and it would be inconclusive if we happen to get 1. All right, let's go ahead and take a look at our first examples. Find the radius of convergence of the sum of n factorial x to the n power. All right, now as you can see, we have an x in here, which is not something we've had before. The biggest thing is we're going to have to keep straight when we take a limit. We're taking the limit of things that involve n, so x will really have nothing to do with anything that's changing as far as the limit is concerned. So let's go ahead and set this up. Again, we're doing this like a ratio test, so it is. The limit as n goes to infinity of the a sub n plus 1 term, which is just plugging in n plus 1 for all of your n's. And then we're going to divide that by the a sub n term, which of course is the given term of the sum. Now, normally we've had to multiply by a reciprocal, but there's no fractions here, so we literally just have to divide by the n term. And then we're going to simplify the inside of that absolute value and take the limit. So we'll have the limit as n goes to infinity. The n plus 1 factorial over n factorial reduces to an n plus 1 in the numerator. X to the n plus 1 divided by x to the n is going to simplify to x in the numerator, which means there's nothing left in the denominator. So what I have here is a limit as n goes to infinity of the absolute value of n plus 1 technically times the absolute value of x. But if you plug in infinitely large numbers into the n plus 1, they approach infinity. So really what we get here is infinity, which means infinity is definitely bigger than 1. So as a whole, this should be a divergent series. The only thing that will possibly make this a convergent series is going to be at the center. And if you remember the formula from the other side, the center was defined by x minus c raised to some power. Well, in this case, there's no x minus c, it's just x, which means that c was 0. So that is our center. The center is 0. So this means because you get infinity here, this series is only convergent at the center, c equals 0. So basically, when x is 0 here, it's the only time this thing is convergent. It's the only time that it's going to actually meet and converge to that same function. All right, let's take a look at example 2. Excuse me, find the radius of convergence of that sum that's given up there. And again, you might actually be able to start hypothesizing whether you think it's going to be convergent or divergent for all real numbers, just one number, or it's going to be some kind of an interval. You can probably start figuring that stuff out if you use a little bit of logic. But we're still going to go through the ratio test. So it'll be the limit as n goes to infinity. Now, remember when I take the absolute value, those -1 to the n power, -1 to the n plus 1, those are basically going to go away because the absolute value is going to get rid of any possible negative sign. So I'm just going to drop that out of there. So it's going to be x to the 2 times n plus 1 plus 1 over 2 times n plus 1 plus 1, that whole thing, factorial, just substituting the n plus 1's in for n. And we're going to multiply that by the reciprocal of the original, which is 2n plus 1 factorial over x to the 2n plus 1. All right, let's simplify before we try and actually simplify the exponents and stuff like that before we actually try to reduce anything here. So in the numerator, it looks like we're going to have x to the 2n plus 2, distributing the 2, plus another 1. So it'll be x to the 2n plus 3, distributing that 2 and then adding the 1. In the denominator, we're going to get, again, you're distributing the 2, so it's 2n plus 2 plus another 1 is 2n plus 3 factorial. And then the numerator on the right fraction stays the same, the denominator stays the same. So now let's reduce. So we've got the limit as n goes to infinity. So the x to the 2n plus 3 over x to the 2n plus 1, subtracting those exponents, is going to give you an x squared. And that'll be in the numerator. And then the 2n plus 1 factorial divided by 2n plus 3 factorial. The 2n plus 3 factorial is really 2n plus 3 times 2n plus 2 times 2n plus 1 down, which means that's that 2n plus 1 factorial. So what you're left with is 2n plus 3, 2n plus 2 in the denominator. So now remember, you are taking this limit as n approaches infinity. We're not plugging anything in for x at this point. So the only thing that's changing is that denominator. The denominator is going to start to grow. The x squared stays x squared on top. So this one is going to approach 0. 0 is a number which is always less than 1. So what this is saying is it makes no difference what value x is. This is going to be convergent. So ultimately, x can be anything, which means that x can technically go from negative infinity to infinity, meaning that your radius of convergence, I affectionately call it the rock, is infinite. the ROC, radius of convergence. It is infinite. All right, again, hopefully that makes sense. Our limit approaches 0, which means it makes no difference what we plug into x in the numerator. Therefore, x can be anything, so the radius of convergence is going to be infinite. It could be any value of x we want it to be. Okay, so we've seen one where we have a radius of convergence, which is basically just at the center. We've seen one now where the radius of convergence is anything. All right. Now, this one got a little bit of different story here because of the fact that the center now is actually at 2. The x minus 2 tells you that this thing is centered at 2. We're still going to try and find the radius of convergence, so let's go ahead and do that. We'll have the limit as n goes to infinity of the absolute value, 3 times x minus 2, all to the n plus 1 power. You have to divide that. Leave myself a lot of room there. Have to divide that by the original, which is 3 times x minus 2 to the nth power. So simplify. So the 3's actually can divide out. So they're gone. X minus 2 to the n plus 1 over x minus 2 to the n just reduces to the absolute value of x minus 2. Remember, when you take the limit, you are taking the limit as n goes to infinity. Well, there are no more n's in this thing at all, are there? So what we want is to say that the limit of this thing is literally just the absolute value of x minus 2, because remember that basically absolute value of x minus 2 is a constant in this case. We're treating it like a constant because of the fact that n here is the thing that we're letting approach infinity. So it's the absolute value of x minus 2. For this to be convergent, we need that limit to be less than 1. All right, so what we have now is an actual absolute value inequality, which ultimately says whatever's inside the absolute value has to be within 1 unit of 0. That's what it means to be less than 1. Well, to be within 1 unit of 0, you can go as far left on the number line as -1 and as far right on the number line as +1. So ultimately, when you have something that looks like this, here we go, that just says that that x minus 2 has to be in between -1 and 1. So that's how we'll set up our inequality. -1 is less than x minus 2, which is less than 1. To solve this, you're simply going to add 2 to all 3 parts. So when I add 2 to the left, we get 1. When I add 2 to the center, we get x. And when I add 2 to the right, we get 3. And does that make sense? It does make sense because we said that this was centered at 2. And if you think about the center being at 2, it's 1 unit from either side to 1 or to 3 to get to the extremes of that interval. So your radius of convergence from the center of 2 out to 1 or 3 is 1. It's 1 unit. That is your radius of convergence. 1 unit from the center to either one of the endpoints. Okay, let's move on to number 4. Find the radius of convergence. So again, we're going to set up, let's go with red, our limit. So let's see, we're going to have the absolute value of -x over 4 to the n plus 1 power divided by -x over 4 to the n power. Now, since those things are both, like the whole thing was being raised to the n, it's probably easier just to leave that in fractional form at this point in time. Okay, so that just simplifies to a -x plus 4 all to the first power. So we're going to have absolute value -x over 4 to the first power, so I don't need to write to the first power. Okay, one thing you should notice is that this is going to be an absolute value, so the negative is going to go away. So really the limit as x, excuse me, that should not be x approaching infinity, it should be n, apologize. as n approaches infinity, once again, the n's are gone. So it's really just going to end up leaving us with the absolute value of x over 4. In order for this to be convergent, that has to be less than 1. So again, I have an absolute value which is less than 1, which means that what's inside the absolute value has to be in between -1 and 1. So -1 is less than x over 4 is less than +1. And if I want to solve for x, we multiply all three parts by 4. So we get -4 is less than x is less than +4. The center of this thing was at 0 because there's no x minus anything up there, it's just x. So from the center of 0, it's 4 units either way to either endpoint. So our radius of convergence is 4. Again, I hope you're starting to kind of get the feel for this. If it's not something that you need to keep watching the rest of these, that is perfectly fine. If you want to watch the rest of them and get the rest of the examples, that is also perfectly fine. Okay, so we'll do our last 3 here, and then we'll get into the actual interval of convergence itself. So we're going to have the limit as n goes to infinity of the absolute value. Let's see, that's going to be 2 times n plus 1, x to the n plus 1, over 3 to the n plus 1, times the reciprocal, which is going to be 3 to the n, over 2n, x to the n. Okay, let's simplify. So I see that on top there I have an x to the n plus 1 over an x to the n. So that's going to simplify to an x on top. I've got a 3 to the n over 3 to the n plus 1. That should simplify to a 3 in the denominator. And then with my n stuff that's in there, if I distribute the 1, it looks like I'm going to have a 2n plus 2 on top. And we'll just have a 2n on the denominator. So now we actually do have something to plug in for the n stuff. So if you look at just this piece alone right here, growth rates on the numerator and denominator are the same, so we can divide the leading coefficients, which is just going to give us 2 over 2, or 1, times that x over 3. So our limit here is the absolute value of x over 3, which once again, there's no n's in it. We want that to be less than 1. An absolute value being less than 1 means that it is in between -1 and 1. So multiplying everything by 3, -3 is less than x is less than 3. The center, the center is 0, so we're good there. So the radius of convergence, it is from 0 out to 3, or -3 is 3 units, so the radius is 3. Okay, a couple more. The radius of convergence. Let's go back to blue. Limit as n goes to infinity. Absolute value, drop the -1 term, so we've got x plus 2 to the n plus 1 over n plus 1 times 2 to the n plus 1 times the reciprocal of the original, n, 2 to the n, over x plus 2 to the n. All right, let's see what happens when we reduce here. So we've got x plus 2 to the n plus 1 over x plus 2 to the n reduces to x plus 2. That will stay in the numerator. I've got a 2 to the n over a 2 to the n plus 1. That'll give me a 2 in the denominator. And then the n parts are just n over n plus 1. So once again, the limit as n goes to infinity of this part goes to 1. So we are left with absolute value of x plus 2 over 2. And that has to be less than 1. So let's go ahead and set our inequality. -1 less than x plus 2 over 2 is less than 1. Solving for x, we'll multiply everything through by 2. -2 is less than x plus 2 is less than +2. And then we'll subtract 2 from each side, so we get that negative 4 is less than x is less than 0. Here, let's actually make that look a little bit more like a 0. All right, and if you notice from up here, again, x minus c gives you your center. Well, the fact that that's plus 2 means that the center was at negative 2. And that makes sense because negative 2 would be directly in between negative 4 and 0. Since negative 2 is right in the middle of negative 4 and 0, and it's 2 units from either one, your radius of convergence is 2. All right, one more, and then we'll stop this video, and we'll come back with interval of convergence. So we want to find the radius of convergence. We'll have the limit as n goes to infinity, absolute value of n plus 1 factorial, x minus 3 to the n plus 1. Let's see, I'm going to skip writing the n plus 1 in the bottom because n plus 1 plus the 5 will actually give us n plus 6 squared times our reciprocal, n plus 5 squared over n factorial x minus 3 to the n. Let's see what happens when we reduce. X minus 3 to the n plus 1 over x minus 3 to the n is x minus 3 on top. N plus 1 factorial over n factorial is going to leave n plus 1 on top. And then I've still got this n plus 5 squared over n plus 6 squared to deal with. All right, so let's see. In the numerator, with just the n's, I'm going to have an n squared out of this one times an n over here. I'm going to have n cubed as my dominant term. In the denominator, we're going to have, it looks like an n squared as the dominant term. So it looks like the numerator is growing faster than the denominator, which means this limit is going to go off to infinity. That means that there is only one place this will be convergent, and that is at the center. And the center, by looking at the x minus 3, is c equals 3. So this will only be convergent at c equals 3. All right, we will come back and we will do the interval of convergence. The good thing is we've kind of already been doing it. We just have to add one extra step.